Yes. Yes. So, good afternoon. I'm waiting for the presentation. Excellent, thank you. So good afternoon, ladies and gentlemen. My honor to be here to present to you about thermoplastics today, carbon fiber reinforced thermoplastics, in particular related to sustainability. It is the main topic, certainly in Europe and the rest of the world, for aerospace industry. And I was very pleased, Mr. Song, with your presentation, very good, on a thermoplastic fuselage. So aerospace, the aerospace industry, it is in a difficult situation, because people want to travel and they will keep traveling. That's a natural instinct. At the same time, we're getting protests. Protests from young people saying, I don't want to fly anymore, it's a problem. And indeed, we are aerospace only a small portion of all the CO2 emissions, but still, something has to be done about this. And what's being done is, for example, the development of more modern engines. Also, if we look at the new generation of aircraft, each time the new generation of engines are, let's say, 20–25% more efficient. This has been the big innovation in aerospace. Today we also see hydrogen coming. This is an example of a cryogenic hydrogen tank being developed. Weight is a very big issue when we're looking at hydrogen tanks, so certainly an area to use carbon fibers. The challenges are it's cryogenic, extremely low temperatures, and of course the weight. So what's happening in aircraft? The engine weights are increasing, the hydrogen systems are being added, and that means we have to reinforce the aircraft structure itself, and then we can carry less fuel or we fly shorter distances. So something has to be done, and the main thing we can do is low weight with composites, with carbon fiber reinforced composites. And it can be thermosets or thermoplastics. But today I'm talking about thermoplastics. And thermoplastics can contribute with respect to sustainability in several areas. First, I'd like to talk about the lightweight. Reducing weight for an aircraft is more than 95% of what we can contribute to reducing CO2 emissions. And of course, carbon fibers, if we divide the mechanical properties by density, show right away the excellent performance as compared to other composites and metals. An example of lightweighting is this panel. It is a complex-shaped panel, for example, for a fuselage of an aircraft, with high-performance, very tough polymers. The low-melt PEEK, PPS, PEC, PEEK. And these very tough polymers, so they're not brittle, they allow innovative designs. At the bottom of the slide is a cross-section of the stiffening technology used in this sample, and the connection between the stiffening elements and the panel itself is purely by the polymer. And because the polymer is so tough, this design is a feasible, certifiable concept. And we are developing this in conjunction with Gulfstream, a customer in the United States. Gulfstream makes business jets. On the left is a conventional fuselage, viewed from the top. And on the right is a more modern fuselage with a very complex shape, which has reduced drag. And the drag reduction means they need 2,000 pounds, that's about 800 kilos, less fuel for a 7,000 nautical mile flight. So this is of great relevance to such a customer, but making these complex-shaped panels in lightweight materials is not easy. So however, if we use thermoplastics, we can create an affordable and lightweight panel shape. After the panel is made, the connection can be done, as shown in the previous presentation by Mr. Song as well, welding the frames to the panel itself. Second example of lightweighting is control surfaces of aircraft. This one is of Gulfstream, but we also do this for other customers, making this in thermoplastic rudders and elevators. And the business case is about weight. So first of all, very strong welds. We see on this picture two parts that are welded together instead of bonded. And if we cover the sides of the picture, it's impossible to see which part is joined to which part. So it's a very strong and certifiable connection. We allow the skin to buckle at 70% of limit load, which means we allow a high level of loading. And this results in a 10% weight reduction as compared to existing composite designs. And then on cost, thermoplastics allow for low-cost processing, especially the welding process. And this gave us a 20% lower cost as compared to the previous design. And this is a certified product approved by the FAA in the United States. On fuselage, Mr. Song mentioned a very nice development here in Korea. In Europe, there is a European Clean Sky 2 project to develop an 8-meter section, a full barrel section of an A320 with Airbus in the lead. And going from aluminium to composite will give a roughly 1,000 kilo weight reduction. And if we think what this means, 1,000 kilo weight reduction means that you have 100,000 kilos of kerosene less consumed per year. So if this aircraft flies for 30 years, it's 3 million kilos of kerosene less, which translates to 10 million kilos of CO2 less for the life of this aircraft. And the wings of aircraft are already composite, the tails are composite. However, the fuselage is a more difficult proposition. So what we are doing here as a group of companies, this lower half is mainly in the Netherlands, the top half is also in Germany, is to show the feasibility of this type of concept, much like KAI is doing here in Korea as well. And this picture shows the welding of the frames of the fuselage. So there is a robot in the middle, and basically, much like in automotive industry, it is moving along and joining all these parts, eliminating the use of bolts. Bolts are cost-intensive and time-intensive. So what else can we do for sustainability? We can reduce the energy that we need in the production process, and we can reduce the amount of disposable materials in the production process. So about energy, typically for large aerospace structures in composites, today we still use autoclaves. And this one is a 3.5 meter diameter, 12 meter length, 4.5 megawatt, so it uses a lot of electricity. So are there alternatives? Yes, there are. So we have invested in some new equipment to process thermoplastics without an autoclave. So to make sheets, to form sheets, or to make complex shapes, and then to create final part quality. And we're doing this in our new technology center in the Netherlands, for which we have invested several million euros in new equipment. For example, laying down the material, in the past it was done by hand. Today there are machines that can do this automatically. For example, with an ultrasonic tacking technology, speeds of up to 2 meters per second can be achieved by these machines. These typical machines make a flat laminate. Then the flat laminate is transported to a press, a preforming press. And in the press, you can make shapes like beams or ribs or otherwise. And then finally, we have a consolidation press, which is basically a machine that can apply pressure and temperature at very high speed to very quickly create a part. For example, this beam or spar of an aircraft component. And early next year, Leonardo in Italy will fly an experimental aircraft. It's called a tilt-rotor aircraft. And in the tail of this aircraft, there will be spars, 3.5 meter spars, made in this technology. And basically, the idea is the green curve is the new process, and the blue curve is the traditional process. So what we are doing is we are shortening the process cycle for thermoplastics. And even though we have to go up very high in temperature, we do that for a very short time. So reducing the cycle time by roughly 80% and the same percentage for the energy we need to make the part. And there is also some development in Europe to develop out-of-autoclave technology with pressure for very large parts. The article in Composites World and also the picture at the bottom is from Simpelkamp in Germany, a large industrial firm that is developing a press technology to basically be able to form a whole fuselage half in an out-of-autoclave technique. So finally, recyclability, also an important topic. In automotive, it's very well established, but in aerospace, it's now becoming more important. So in Europe, we are going towards fully circular materials by 2050 and 50% less use of virgin materials by 2030. And therefore, we have joined forces with several companies and institutes in the area of thermoplastics processing. And the idea is to collect the waste from the factory, so the manufacturing waste for certain parts, and to grind them and then to compression mold, much has already been explained earlier today, to make parts. And for example, these panels, access panels, or even more complex shapes can be made. The performance of the material of these parts is much lower than the original material, but acceptable for these small parts. And if we look at energy consumption, as I mentioned at the beginning, more than 95% of the contribution towards CO2 emission reduction is by weight reduction. So on the graph on the left, we see a number, 200,000 kilo CO2 equivalent. That's what you save typically with a small component over the life of the aircraft. If we look at how much we save in the manufacturing itself, it's much lower. You see 2025. So it is the largest part of the contribution towards CO2 emission reduction, if we fly on kerosene, is weight reduction. In the future, when we go to electric flight and hydrogen, it's a different story. Then this becomes much more important, and that's the manufacturing and the end of life of a composite part. So my company's view on the future is that very small aircraft will be electric powered. The mid-range aircraft, airliners, will be hydrogen powered, and the long range will probably be sustainable aviation fuels, so biofuels and the like. And today there is this new market segment, and that's also very relevant here in Korea. In Korea we have Hyundai working with Supernal, and Hanwha working with Overair, creating these wonderful new electric vehicles. The predicted production volumes are truly large for aerospace, so 5,000 plus per year per manufacturer. They are at the moment fully electric. They might be hydrogen in the future, but for the moment fully electric. So it's a bit different from what we are used to. The use of batteries and vertical takeoff and landing means the weight of the aircraft is very, very important. And the high build rates means that the cycle time of a production process must be very short. So some of the manufacturers are leaning towards thermosets, others towards thermoplastics. So I think both technologies are viable. We have a nice example here. We are working with Joby Aviation. Joby Aviation is, we think, the leader of this segment currently, and they have a strong interest in high-rate, low-weight products. And I'm very proud to show you that we will be manufacturing, as of next year, the control surfaces of this aircraft. So the ailerons and the ruddervators of this aircraft, they will be thermoplastic. It is a out-of-autoclave production technology, basically consisting of two elements, and the elements are welded together. And this is a picture at the Paris Air Show. The gentleman on the right is Joe Ben Bivert, the CEO of Joby, very proudly announcing the product. So I would like to finish my presentation with something about culture, totally different, non-technical. So the Netherlands, you can see it in red. It's a really tiny country. We have 17 million people, 17. It's 1/3 of what Korea has, South Korea. You have 50 million people. But maybe there's a similarity, because if you are a small country, you should be good at something, just a few things. And this is what the Netherlands is good at, you may know. And there's one more picture coming, this one. So on the top left, I don't know if you recognize it, but it's a machine from a company called ASML, spin-off of Philips. They're a world leader in the machines that make the chips, the wafers for chips. So it just shows that if you are concentrating on a few things, you can do a very good job. And for ourselves, it is thermoplastic composites is a focus in the country with a big supply chain, and also electrical wiring systems with high power, high voltage. I think this is the final one. So why is the Netherlands successful as a country? And maybe there is a similarity with Korea. Is the Dutch people are outgoing, they like to travel, they want to go places. Anti-authoritarian, don't just accept what everybody says. Also, it's an advantage and a disadvantage. And then there is a consensus culture. The Netherlands is a country that if we don't manage the country, it will be underwater. So you have to make a deal with each other. Then we have good institutions for education, and luckily our government is very supportive currently. Yes, this is the Dutch ecosystem working together, so material suppliers, universities, industrial companies working together in national and European projects, and spread out over the Netherlands as a country. My conclusion of this presentation is that thermoplastic composites can and will contribute to a more sustainable future in aerospace by, first of all, by lightweighting, extreme lightweighting, by reducing the energy use for this, and also reducing waste during production and offering full recyclability. At the same time, it's still at the start of its life cycle. It's taken a long time, but the potential is there and it's very large. So with this, I'd like to thank you very much for your attention. Thank you.
Thank you for your great presentation. And we have 10 minutes remain. Okay. So is there any comments and questions in the audience?
Thank you very much for your presentations. It's quite interesting. I have two questions. The thermoplastic, regardless of the matrix type, regarding the thermoset or thermoplastic, we are aiming to make a sustainability. Sustainability means completion of recycling. Recycling means not only the carbon fiber recycling, also matrix recycling. So what do you think about the recycling of the thermoplastic regarding the process like pyrolysis or solar bliss? Pyrolysis is not really sustainability because it's making some emissions. So what about that, the process? Are you expecting 100% separating and recycle matrix and recycled maybe short fiber? There are things to make it sustainability. We have to think about the not petroleum products, so bio-based thermoplastic. Do you have any R&D activity for bio-based thermoplastics?
Yeah, thank you for your question. The first one about recycling. So for thermoplastics, there are two possibilities. One is what I showed here, going for full recyclability by reprocessing to a lower quality material. At the same time, working with a sulfolysis process should be possible in principle, and that would be fairly parallel to the way you work with the thermoset composites. Let's see, the second question, could you repeat the second question?
Second question, to become, make a real sustainabilities, are you have some activity or R&D activity based on the bio, based on thermoplastic?
Yeah, so we are very interested. We do not have any serious activity currently because as far as we know, the bio-based materials are not able to meet the standards that exist for structural application of composites. However, if that were to be feasible, we would be very, very interested. Yes, thank you.
Another question? Let me ask you. GKN and many engineering group and company have been working thermoplastic technology development. But currently, not many real aircraft adapt this technology. So what kind of hurdle is existing in technology point of view and certification point of view?
Yeah. So I think thermoplastics is an example of a technology with a lot of promise. However, you must execute all the work needed to prove your technology, so not only manufacturing, but especially also design and certification and qualification. And this takes a lot of time, and it also takes convincing of customers. And some customers are more inclined to adopt innovation than others, so it just takes a long time, but I don't see any reason in principle why this technology could not be very successful to a large extent. Yeah.
So technology is ready, you think?
Yes, so if we look at, for example, fuselage,
Yes.
you discussed it, I discussed it.
Yes, right.
I think for fuselage, let's say for what we are developing is a non-pressurized aft fuselage of this business jet. That is almost ready for market introduction. If you look at the pressure cabin, there's, I guess, some more work to be done in certification and qualification to really prove to the authorities that it's feasible, that we have done all the work. So it'll take a few more years, but it should be in step with the next big program for example, Airbus or Boeing.
Okay.
Yep.
And when I studied induction welding process in KAI,
Yes.
It's too difficult to uniform to maintain the uniform temperature on the surface, bonded surface. Sometimes it means how. Have you figured it out how to uniform the temperature on the mating surface, and bond width is also
Yes.
compromised to certify the bond property?
Yeah. So we have developed this for fabric-based materials. So I showed a rudder elevator application that's with a fabric-based material, and that works very well. For unidirectional tape, it's more difficult.
Right.
So that's a challenge, I think, to work with tape
Yeah.
in induction welding. Yeah.
Any other question? Okay. Give him a big round of applause again.
Thank you.
Thank you, Paul.